Okay, let's look at the oxygen hemoglobin saturation curve and what that actually means. Now, you may recall if you've been in a hospital or a doctor's office, they will often put something on your fingertip with a red light on it, and you will see a number associated on a monitor, and it will say 97 or 98%, and that's your oxygen saturation. So what exactly is your oxygen saturation? Well, if you recall, going back when we looked at red blood cells and more specifically at the hemoglobin, I think it was earlier this semester, might have been last semester, where each hemoglobin molecule, each protein of hemoglobin has 4 atoms of iron. Each atom of iron has the ability to carry or bind with a molecule of oxygen. So each hemoglobin can bind with 4 molecules of oxygen. And what the interesting thing with hemoglobin is when the first oxygen molecule binds with hemoglobin, so if we have 4 different ones, the first one binds with it, and that causes a conformational change, or a change in the physical shape of the hemoglobin protein, the molecule, okay? And when it changes its shape, it allows for that second oxygen to bind even easier. That changes the shape again, which allows the third oxygen molecule to bind yet even easier than the second one, and then it changes the shape for the 4th time, making the last molecule bind even easier. Okay? This is called the cooperative binding effect of oxygen. So the first one is the hardest one to bind to hemoglobin, but as that changes its shape, it makes the second one, the third one, and the 4th one sequentially bind even easier. And the reverse is also true, is when the first oxygen comes off, again, it changes its shape, allowing the second oxygen to disassociate with it even easier, changes its shape, then it's even easier for the third one, and then the 4th one. So this is what we're looking at on the cooperative binding effect of oxygen. And that's oxygen saturation. Now, what is saturation of this? We said that each hemoglobin can bind with 4 molecules of oxygen. So if all 4 atoms of iron were bound with oxygen, that would be 100% saturated. And if 2 of them were bound with oxygen, that's 50% saturated. And if only 1 is bound with oxygen, that'd be 25% saturated. Okay, I think that kind of makes sense. So let's look a little bit closer, and how do we determine what the saturation is? Why do they put that thing on your finger? What's that number really refer to? Now, there's a few different things that can determine the saturation of this. The partial pressure of oxygen is going to be the most important factor in determining the saturation of hemoglobin. There are other things like temperature, the hydrogen ions binding with hemoglobin, carbon dioxide binding with hemoglobin, those sort of things. But we're going to look at primarily the partial pressure of oxygen, and we might go into the temperature as well. So let's look at this. And this is your oxygen saturation curve. Okay, you can see this red line here. It's kind of it's not a straight line, it's kind of an S-curve shape, okay? The bottom axis here is talking about the partial pressure of oxygen. The vertical axis on this one is the saturation of hemoglobin, okay? So we know that the partial pressure of oxygen in the alveoli is 104 millimeters of mercury. So this would be, let me do this in green, okay? So 104, this is roughly this dotted line here, okay? Coming all the way up, and it comes over here, okay? So it's not at 100%, but it's at 98%. So if you go on the right-hand side, you can see this column here. So a partial pressure of 100 or a partial pressure of 105 of oxygen yields 98% saturation of the hemoglobin. Well, let's look at why it's not 100%, okay? If you were to start removing some of that oxygen, okay, and it disassociates with it, if we have, let's say, 80% partial pressure of oxygen, so now it's already going through your system, oxygen is coming off, 80% saturation coming straight up is roughly at 95%, which is consistent with that number, okay? Now, even at low percentages, because the partial pressure of oxygen in your bloodstream, once it's transferred over, that was 40, what am I looking at? 40. Okay. So at the tissue level, we have too many numbers here. At the tissue or cellular level, the partial pressure of oxygen is 40 millimeters of mercury. And you can see at this point, 40 coming straight up is roughly 75% saturated. Well, now you ask yourself, why isn't the saturation even lower? Don't we want to give up more of that oxygen for use of oxygen in the tissues? Well, no. Let me look for the correct term here. Okay. The reason we don't want to give it up, it's called oxygen reserve. Okay. So normal activities, you can disassociate about 25%, 25% of oxygen from your hemoglobin. The remaining 75% is there in reserve. That reserve is used for when you are undergoing stressful exercises where you have a demand for it. That demand can take down your partial pressure of oxygen, or it can be used by your muscles and so forth way down to a 20-30% level. And as you can see, that's around 35. Let's see, 20% is 35, okay, at this one, 30 is 57. So this is roughly the area that you're looking at that the oxygen reserve could go back down to, okay? So this is your oxygen hemoglobin saturation curve on this one. So this is something that you will need to know or at least have a basic understanding of what this is referring to. This will come into play a little bit more when you get into pathology. So now let's look a little bit at the temperature. So let me hold on just a second. Let me get a picture for the temperature. Okay, let's look at a couple other things and put it into terminology that you're going to likely hear in future classes, okay? So we know that the oxygen hemoglobin saturation curve gives you that S-shaped curve, okay? So the higher the partial pressure of oxygen, the more saturated the hemoglobin becomes. Now, at sea level, we talked that the partial pressure of oxygen in the alveoli was 104, and the maximum saturation you're going to get is 98%. So how do you get it to 100%? You would have to increase the partial pressure of oxygen. In order to increase the partial pressure of oxygen, you would have to increase the atmospheric pressure. Okay, if you increase the atmospheric pressure, that increases the partial pressure, and I believe that would be like 3 atmospheres. Okay, so you would have to be below sea level in order for that to occur. Climbing a mountain, you are decreasing the partial pressure of oxygen, so therefore you would have less saturation. And people climbing mountains, when they have lower saturation, they can have conditions like altitude sickness, headaches, nausea, confusion, and other issues. So let's look at two other things here, which is how does temperature and the pH have an impact on that saturation curve. So what we're looking at on this table right here, we're looking at, let's just look at this first. Let me make sure this, I'm going to get my pen working here. Okay, so we want to look at, there we go. We want to look at this one here first, okay? And this is going to be associated with temperature. So you can see on this, the blue line, the center line here is your partial pressure of oxygen, and on the horizontal you have the saturation of hemoglobin on your vertical, and the blue line, the center one, is based on temperature. So let's look as to how temperature is affecting the saturation curve. If you increase the temperature, increase your body temperature, that causes the hemoglobin to change shape or not want to bind with oxygen as well, okay? So it will release the oxygen easier. If you release the oxygen from the hemoglobin, the saturation goes down. If you lower the temperature, you increase the affinity of hemoglobin to attach to the oxygen, thereby increasing the saturation. So at 38 degrees, let's see, 38 was 100, I think it was 100 degrees Fahrenheit, 100.4, something like that. So at 38 degrees, 40% partial pressure of oxygen gives you 60% saturation. If you maintain the partial pressure of oxygen at 40, but you decrease the temperature, you can see that the saturation is much higher, okay? Closer to the 95-98%. Though if you increase the body temperature, same partial pressure, the saturation at this point is around 60. So what this is, as you can see, let me use blue here. So if this is your saturation curve, it's a really poorly looking saturation curve, and we have one to the right of it, and then we have one, let me do purple over here. Okay, so here's the vertical line. I know this is getting really squirry. Okay, so it's kind of like this. So if the curve is to the right of your normal curve, that is called a shift to the right. Okay, that terminology you will hear again, especially in pathology. It's called shift to the right or shift to the left. So the other one, if the curve is to the left of the normal, then it's a shift to the left. And if it's a shift to the left, then you know that the hemoglobin has a greater affinity for oxygen and therefore have a higher saturation. If it's a shift to the right, the hemoglobin is less likely to bind with the oxygen and therefore less of a saturation. So body temperature can cause a change. The last one that we're looking at is going to be the pH, and the pH is associated in part with the hydrogen ions. Okay, so just as before, a shift to the right, less affinity; a shift to the left, a greater affinity for oxygen. But a lower pH, more acidic, okay, because you are retaining hydrogen ions within the hemoglobin. Because remember, when carbon dioxide comes into the red blood cell, it will disassociate. Part of it becomes bicarbonate ion, goes into the plasma. The hydrogen ion stays bound to the hemoglobin. Okay? Well, if you keep that, then the pH lowers, becomes more acidic, and that results in a shift to the right, meaning it has less affinity for oxygen. Okay? Less affinity for oxygen, lower the saturation. The higher the pH, the more alkaline, the greater affinity, and then that's associated with a shift to the left. So that's the basics of this. Pay attention to the shift to the right, shift to the left, what that is referring to, okay? And I think, let me just, I think for our purposes right now, well, if there's another video right after that, you'll see it on Moodle. But I don't know if I'm going to do another video. So until then, stay tuned.